Okay, welcome back. Today we're going to look at some special triangles and more importantly to us, the special angles that result from these triangles and how they relate to trig. So if you go back to sort of the first time you saw triangles and put them up on the board, probably in about grade 1, maybe before that, kindergarten or even younger, and the teacher said, or your parents or your guardians or your older siblings said, what's special about these triangles? And you'd say, the sides are the same. Okay, so sort of two special triangles, the equilateral and the isosceles, are kind of are the basis of what we're looking at today. We know that with trig, or at least with the primary trig ratios, we're looking at right angle triangles. And so obviously in this isosceles triangle, it's pretty clear. We have a right angle down here. And of course the key to the isosceles is these two lengths are the same. With the equilateral triangle, the right angle's not there. But if we kind of fake it and sketch in a right angle right there, what we end up with is, we end up with two triangles, each of which, that work? That's pretty light. Each of which ends up having a right angle in it and being kind of special cases. Well, that's not showing up very well at all, but that's okay. You can sort of see the right angle triangle that resulted here. And these are the two triangles that I'm really interested in for today. This half a triangle here, and of course the isosceles. So, if I'm looking at these, what's sort of key to me is, and this is something you would have done likely in the past, but the angles on the inside, I'm going to pause here, my alignment's way off. Okay, so as we said, an isosceles triangle, we know, at least if there's a right angle in one of the corners, the other two angles have to be 45 degrees. They always have to be the same. And so if 90 is taken up, of course, 45 is what I'm left with. Referring back to the original, what was an equilateral. In my original diagram, I would have had three angles here, here, and here, each of which would have been 60 degrees. And so the angles that I'm interested in now, still 60 down here. And of course, if we have 60 there, 90 here, I'm going to have a 30 up here. Okay, so this is kind of why 45, 30, and 60 are angles that we consider special. The equivalents of those, now that we're dealing with radians, if you need to, you can work it out from last day, but essentially pi over 6, pi over 3, and pi over 4. Remembering that pi is equal to 180 degrees, and so 180 divided by 60 gives me that 3, or sorry, 180 divided by the 3 gives me the 60 degrees, 180 divided by 6 gives me the 30, and so on. Just a quick little reminder of the cast rule. Again, whatever you want to remember here is fine. All soup turns cold. I've heard all students take calculus. Just remembering cast starting down in the fourth quadrant is fine. All silly Trekkies cower at the threat of the dark side. Anything like this that helps you remember that those are your various sections. And of course what they mean again is all of my ratios are positive up here. Sine is positive here. Tan is positive here. And cosine is positive here. Didn't actually mention this last time, I don't think, but you want to recognize that if we are talking about our reciprocals, the reciprocal of sine is cosecant, And since cosecant is simply 1 divided by the value of sine, it will be positive in the same area as is sine. Same sort of thing. Sorry, secant is positive down here, and cotan is going to be positive here, still all positive there. Little introduction here, what I've called the butterfly rule, or what I refer to as the butterfly rule. Again, sort of not a real rule. If you did try to look that up in the back of a math textbook, I assume you're not going to find it, unless it's one that I've written, and I don't think any of those exist. But the basic idea of it is that any line, essentially, that you run into that can be drawn up this way. So if I have an angle of whatever gets me to this first line, to the second line, to the third or fourth line, whether it's a positive angle that goes all the way around to the line, or whether it's a negative angle that comes the other direction, the ratios sine, cos, and tan are all related, and they're all related based on, oops, didn't mean to do that. They're all related based on the original angle in here. So as an example, if we think in terms of radians specifically, and I'm looking at this angle to here being 3/4 of pi, or 3 pi over 4, which leaves me with 1/4 pi, or pi over 4, being sort of the angle from the line that we reached to this kind of magical endpoint, the 180 degrees, or the pi degrees. Sine of 3/4 pi is going to be exactly the same as sine of pi over 4. And if you needed to, you could test that by punching it into a calculator, either with radians or with degrees, the equivalent being sine of 135 degrees should be exactly equal to sine of 45 degrees. And the reason for it is basically that this, this triangle and this triangle are identical, other than the fact that they're facing opposite directions. And so when I have this 135 degree angle, it forces me to have a 45 degree angle in the second triangle. And so the lengths of all the sides, you can see that this side and this side are identical length. This side and this side are of identical length, as are this side and this side. And so the ratios, which are made up of any two of those sides, of course, would have to be the same as well. And so what we're suggesting then is, if we know this angle over here, and we're asked to find this angle right here, it's simply a matter of recognizing that the 3/4 pi and the pi over 4 are related angles, and that in the area where the 3/4 pi occurs, in this case the second quadrant, sine is positive, and then when we look at cosine and tan, of course, other than the negative symbol here, they will be the same as well. Cosine of 3 pi over 4 is going to be exactly the same as cos of pi over 4, except that in that quadrant it is negative. And the reasoning again is the same. I have the same adjacent in both cases size-wise. I have the same hypotenuse. However, on the actual grid here, these are negative x values. These are positive x values, and so that's where my negative comes from. I have the negative of the original adjacent. I have a hypotenuse, which is the same size, and so I guess I could leave that one on. And so the original, whatever the calculation would have given me if I had used pi over 4, I'll simply get the negative of that with 3/4 pi over 4. I think I need to sneak one more thing in here. That's not what I meant to do. And so, kind of lastly here, if we think about those original two triangles, the 45 specifically to start, if I'm looking to find sine, cos, and tan, and I want exact answers for them. Okay, so this is going to be the key. I don't want to punch this into my calculator and get 0.071. 7071. What I want is an exact answer for sine of 45 so that I don't lose accuracy when I try to use it. So when I think back to the 45-degree triangle, I recognize that this length and this length are the same. So if I pick a specific triangle to work with, maybe the easiest one would be one where each of those lengths is 1 unit. 1 inch, 1 centimeter, 1 mile, doesn't really matter. If those are each 1 unit, if those is each one, using the Pythagorean theorem, I can find the missing side. And it's a pretty quick little calculation, 1 squared, 1 squared. So c squared is 2, c is root 2. Okay. And I'm going to leave that as root 2 because I want to have exact answers. When you punch root 2 into a calculator, you get something like 1.41, I believe, but it's not really exactly that number. It's 1.41 whatever, 38, and it keeps going. It's a never-ending decimal, and so I can't really get an accurate answer without leaving the root 2 alone. So sine of 45 then, kind of starting from this key point, sine is my opposite over my hypotenuse. So sine of 45 is equivalent to 1 over root 2, which, just so you know, is the same as root 2 over 2 if I multiply top and bottom by root 2. Just in case you ever see it written the other way, sometimes you may, and it may throw you off. Cos of 45 is 1 over root 2 as well. It's the adjacent down here over the hypotenuse. And tan of 45 is opposite over adjacent, 1 over 1. So these are my exact and my special ratios for my 45 degrees or my pi over 4 degrees, depending on whether I'm working in degrees or radians. Similarly, if I wanted to work with the other special triangle, which is the half of the equilateral, this isn't very accurately drawn, but that's okay. I've got my 60 degrees down here, my 30 degrees up here. There's one ratio I always remember, so that if and when I'm actually asked to find these values, I can do it. Sine of 30 is exactly 1/2. So for 30, my opposite is 1, my hypotenuse is 2. And then similar to what we did over here, if I work backwards, I can find the missing, this is 2 squared, this is 1 squared. I can find the missing third side, and this is 4 minus the 1 from over here is b squared. So the missing side is the square root of 3. And as I did with sine, cos, and tan of 45, or pi over 4, I can do the same thing now with sine, cosine, tan of 30 and 60 as well, because they're right in this diagram. 60 is here, and so that's its opposite, that's its adjacent, that's its hypotenuse. I just pointed to them, you couldn't see that, but that's what I did. For sine of 30, same thing. Opposite over here, adjacent, and hypotenuse. And so if I want to write any of the ratios, they are right there ready to go. So quickly, cos of 30 is the adjacent, which is root 3 over the hypotenuse 2. Tan of 30 is the opposite 1 over the adjacent root 3. And for the 60s, sine of 60 is going to be the root 3 over 2. Cos of 60 is going to be the 1/2. And tan of 60 is going to be the root 3 over 1, or just root 3. Okay, so what's going to be important to us is to be able to reproduce these two diagrams and find those missing angles or those missing ratios if we don't have them. Again, I don't suggest memorizing a whole bunch of things like this, because as long as I know how to draw the 45-degree triangle, which is very simple, two sides of the same length, and then calculate the third side, and as long as I can remember essentially one angle over here, 30, or again, pi over 6, being 1/2, then I can reproduce the triangle to get those missing, to get those special angles. And unfortunately, it will be kind of your responsibility to know those, or to be able to get those, whether it's draw these triangles onto your test paper and work from there, or actually memorize them. Those are basically your two options. There will be questions for sure where you need to use the exact values somehow. Okay, so finally, determine the exact values of the 6 trig ratios, 5 pi over 3. So the textbook is going to give you a slightly different answer. I like this way of doing things a little bit better, but certainly if you've done these before using what you see in the textbook, that's fine with me as well. 5 pi over 3, if we're thinking about where that's going to get us, you sort of have to have a pretty good idea of where things are. This is, of course, pi over 2. This is pi. This is 3 pi over 2. And this is 0 or 2 pi. So 5 pi over 3 will take me past this and around to over here somewhere. So 5 pi over 3 gets us all the way around into the fourth quadrant. If we think about it in terms of the butterfly then, the special angle, the angle that's kind of important to us, is the pi over 3 that's left to complete the circle, which is equivalent, if we're interested, to 60 degrees. Of course, we don't necessarily need to know that, but sometimes making that reference is not a bad thing. We're still going to be more comfortable with degrees most of the time, so being able to go back and forth is a pretty valuable thing. So, asked to find the trig ratios then. And so we recognize that sine, cos, and tan, well, and the other two as well, sine of pi over 3 is going to be equivalent to what was sine of pi over 3. However, because I'm in the fourth quadrant now, I want to recognize that down there, sine is going to be negative. And so what I do know is that sine of pi over 3, which is the equivalent of sine of 60, is root 3 over 2. And so sine of pi over, 5 pi over 3 will be negative root 3 over 2. Similarly, if we wanted to finish up the others, cosine of 5 pi over 3 is exactly equal to, in this case, because cosine is going to be positive down here, it's going to be exactly equal to cosine of pi over 3, which is exactly 1/2. And we can then continue to finish up what is tan, what is cosecant, what is secant, and so on. So video is running pretty long here, so just sort of a quick note on, I'll do cosecant here. Cosecant 5 pi over 3. You want to recognize is the same as 1 over sine of pi over 3. So it's essentially 1 over the negative root 3 over 2 from earlier in the question. And when we do this math, this is a good little exercise, it's 1 divided by negative root 3 over 2, which is 1 times, flip over the second term, negative 2 over root 3. And so cosecant is negative 2 over root 3. Okay. And if we sort of pay attention to what we did then, it seems pretty reasonable. I could have done a little bit less work here, that cosecant is, if cosecant is the reciprocal of the original value of sine, then flipping the answer I have here will get me to my answer for cosecant.